So, welcome to the DassaultSystems vendor session. I'm here with my colleague, Christopher Stromberger, Quentin Prieto. I will talk about the usual recent features of Daimler for the last couple of years. Then they will go into more the application aspect of it and some demonstrations. So, all right. So, what have we done in terms of model development? So, of course, half of this you have already seen because Leo took it as part of the LTX presentation. Variable length parameter arrays. This is a really nice feature. It's not standard Modelica, hence this Daimler unknown array annotation, but we are going to propose it to for standardization in Modelica eventually. It's a really good idea. It works in Daimler, it works in the generated FMUs. Super cool. Parameter records, we think that best practices is to have parameter records and then propagate those records into your model. We have a convenient feature there. You can import SSV files or CSV files and create those parameter records. So the Daimler import creates the Modelica code for the records. Simulation speed, always a topic that people like. And here is Hans, who is responsible for most of that. So, for example, with the thermal fluid streams, for example, we did improvements on code generation for Modelica functions and for calculating outputs. So, yeah, like a 2 or 3 times performance improvement compared to that. Anybody from Julia here? Julia Hub? No, because just remember that Julia Hub always says that Julia Hub is 500 times faster than Daimler. Whatever. Fine. Nice feature is that we have a new feature that you only generate code for the outputs of your model. So if you have large chunks that are not connected to the output, or if you select that only connect certain parts of the output, you can eliminate huge parts of your Modelica model because they do not affect the output. And that can even help with some stability issues. Co-simulation technology, a new feature that we are going to present here. Co-simulation technology that we developed together with our partners at TLK Thermo. The idea is to smooth the inputs to allow the co-simulation solver to not restart as often. So I'm making here the claim that the simulation runs 400 times faster. Is anybody skeptical here? So if you are skeptical, we invite you to go to the presentation tomorrow at 10:20 because then we are actually going to prove the claim. So you are welcome to criticize us, but please wait for Erik Henningsson, who will take the blame. Parameter optimization. We have for a very long time had an optimization library in Daimler, which, let's say, had a user friendliness on the low side of the scale. But we thought that, okay, we can make a really nice user interface for the simple cases. So we did it, and it looks like kind of the sweep parameters case stuff or the Monte Carlo stuff, the same stuff. Doesn't solve all the problems, but it's simple solutions for the common case, you know. Yes, Monte Carlo simulations improved in steps. We now have a much nicer visualization of the trajectory analysis with mean value and standard deviation and prediction interval. Make sure it's much nicer. You can do the global sensitivity analysis. And also we are using Latin hypercube sampling by default, which has proven very powerful. SSP and EFMI. SSP 2.0 is supported in Daimler. We also support, which has been enabled now in SSP, that you can use Modelica components and a causal modeling as a consequence, better FMI conformance, and so on. There is a new standard that came out last week called SSP Layered Standard Traceability. We support much of that in Daimler, and will especially in the next release that is coming in November. One of the major improvements of SSP support is that this read, modify, write cycle actually works. And that's kind of a good improvement. Works at least partially. I'm looking at my colleague from Robert Bosch here, who has comments. Yes, improved SSP conformance, cross-tool compatibility, especially between Daimler and EasySSP. We have found some issues with the SSP specification in the process. That's good. And I would like to emphasize that the ITEA Open Scaling project is using several of the technologies that are going to be presented here at the conference, and the uncertainty quantification, and also using SSP as well, parts of the work. I think that's valuable. FMI for embedded systems, you will see a little bit of that. So you got the, let's say, the front-end parts of EFMI in Daimler. We generate GALEC code, and then there is a separate DS product for code generation according to all these standards. It's called software production engineering, and yeah, well. Improvements, for example, integrated Clang tidy and CPP check. So you can do your checks of the generated code according to those specifications. So yeah, we'll see example of that. So version management, you might have seen that Daimler has integrated support for Git, for example. You can do the same stuff, but use our so-called 3D experience as a repository instead of Git, which gives you seamless integration with the platform tools and the cloud simulation. One of the nice new features is this graphical display of the hierarchy of the tree. And here is the low-tech evolution of Daimler. Daimler without any user interface at all. If it's good enough on Linux without X, then it's good enough for you. Okay, it has some limitations, but it can translate and simulate model, run scripts, and it supports the Python, Java, and JavaScript interface if you want to do Excel simulation. So, except for nostalgia, the idea is that you are now able to easily use Daimler in your own tool chain. So, I mean, you don't have to bother about the user interface. All the error messages are sent to standard error output, so it's easy to integrate. And in an X environment, you don't even have to have X installed on your server. You can run DMC otherwise. In the picture is a Teletype 33. Hands up, anybody who has used a Teletype 33 in their lives? Oh, well. Ah, yes, there is another one. Yeah, I'm glad. So, next Daimler version coming out in November, I think, has MSL 4.1 as default. You can get 4.0 as a compatibility package. It has more efficient FMU import with less generated Modelica code and less generated C code. Great improvement. Smaller code for array equations. Good stuff. On popular request, you can now customize the ribbon and the quick access toolbar, which is saved to the next session. Better SSP support, obviously, gradual improvement. And we have a feature where we have preloaded some popular free libraries in Daimler, or not preloaded the library, but we have a list of libraries, free libraries. It's incomplete, and if you want to be on the list, you can contact me and make an argument for that. But, I mean, if you want thermofluid streams, for example, you can click it there and select it from list and download it and install it. So, but it's work in progress. It's not complete. And we're aiming at free libraries on GitHub at present. Modelica libraries. We have lots of libraries for several domains. The best news is that we now have the complete TIL suite as part of the Daimler portfolio. We used to have something called thermal systems, which was kind of a subset, selected subset. Our users thought that was crap and wanted TIL suite instead, so we gave them TIL suite. At DS, it's exactly the same libraries as the ones you get from TLK. We have packaged them in bundles that we think that are attractive to the users. If you have an old license of thermal systems, you can get a free upgrade, which gives you a TIL base plus TIL air conditioning library. It's free, but you have to ask for it. And we have a new library coming out, Sustainable Supply Systems Library. It's a limited complexity library, so it's not detailed simulation of different stuff, but it covers a broad range of energy applications from mining, energy storage, energy production, all sorts of stuff, rail applications, data centers, and so on. So, for example, here's an example with mining trucks. Does it pay off to electrify your mining trucks? The short answer is yes. What do you want to do with your house? So we can have renewable energy sources connected to a battery storage, to the grid, etc. You can simulate that. And now, applications.
So we thought of showing also some applications that recently we successfully developed. One is on EFMI. I'm not sure Christoph gave the tutorial on EFMI, and it's an FMI for embedded systems. And there in this demonstrator, we thought of, okay, how can we set up something easily? So we decided to use an Arduino board, which is low budget, so Arduino Uno compatible, and try to deploy successfully an eFMU on it and run it, of course. And so the idea of this is that we have a battery cell model in its core, which should be then later on be seen as a virtual sensor. So we are tracking the cell core temperature that is computed during the simulation. So normally you would have maybe your real cell that gives you measure some input signals like the load on the terminal, maybe the ambient temperature or the temperature on the surface. You feed this in for the eFMU, and then you compute the cell core temperature, which would be hard that you put a sensor inside the cell. So here in this particular use case, we just used it virtually, and the inputs are a power request that comes from the user. You can select a power request from the battery, and you can play with the ambient temperature to speed up a bit the cooling, because here we want to see some changes in seconds, and normally you don't want that your battery cell is exploding or something, so we speeded it up. And it's pretty nice that together, of course, big effort from Thorsten Sommer and Christoph Bürger, that this successfully was deployed. So the idea is then with the virtual battery cell model in combination with a simple controller which tracks the battery temperature and then limits the power depending on the current temperature, cell core temperature. You see here we use the battery Daimler DS battery library for modeling the cell, which currently just looking at electrothermal behavior, but theoretically if aging would be interested, but probably it's not something for real-time simulation, because aging we would probably stop at some point, compute then the state of health of the cell. So a lot of different use cases we already have in mind, but here this we already successfully deployed on the Arduino. You will see soon a video where the tracked signals in combination with the Arduino board are running. And if you're wondering, there are status LED where the green says, okay, temperature is good, everything fine. This kind of purple magenta color is saying, okay, we are now in a power limitation process, and red means, okay, we cannot request any power anymore, it's limited down to 0. That was the idea, and to prove that it also works, we have it on our booth as well, so you're welcome to join us and play on your own with it. So it's really implemented it. And there is a short video. Okay, so this is an Python UI to better see then the real signals that come in and are computed by the EFMU. See on top the status, LED, and then if you start, you see now everything is fine. This green in the middle plot, the green line, when we hit it, then it starts derating, and the purple line in the middle plot will then be the maximum limit and will completely lower the power that we can request. So we see here, we start in the power limitation phase. As the controller is smart and directly reduces then the power, we need to a bit play with the ambient temperature to force the system to heat up to its maximum. And now we see here now, the next step, it gets red. It's real-time simulation live. As said, it's on the booth. If you don't believe that we set it up, please come play on your own with it. We are happy here. It's pretty nice, and it shows that already with, let's say, a cheap and not so complex setup, because when I hear EFMU and get more into it, it was a bit complex. I thought always, we need high sophisticated microcontroller boards, a hill setup and super fancy stuff, and already this works. We can hear multi-physics on an Arduino board, which is, I don't know, you get it almost for free, and you can already start to play with Daimler on an Arduino board, which is pretty nice. So this, okay, not the big hands. Let's get further. So the other application we want to show, which exceeds a bit the scope of Daimler itself, also a bit towards CFD simulation, is a combination of a Daimler HVAC model, which was tested with different libraries. We also use the HVAC library from XRG or with TIL, where different versions, depending on what is interesting, specific component sizing, or more the general computation of the HVAC system. And this is, the HVAC system is modeled in Daimler, and it exchanges with a 3D model, 3D CFD model of a server room for a data center information. And in this 3D CFD model, you really get a feeling of the temperature distribution in 3D in the server room, which is also pretty nice. And of course, only a video shows the big value of it. So we see here that there comes the cold air from the bottom side, and it starts heating up. It gets from the top out of the system. Here it's the proof that there's really Daimler behind. And then we see here the animation of the 3D CFD model. So we see that it starts now heating up. And especially then, depending on the server load and how the HVAC system is designed, we, for example, see the very, as indicated by the color, the dark red means that there are hot spots that needs to be fixed, because this might cause a server shutdown, or something needs to be better cooled. And this was really showing big value besides the, let's say, 1D world coupled directly with the 3D world.
So, hello everyone. So what I'm going to present to you now is a use case we had at a customer from the food and beverage industry. And in this workflow, we were using versions of Daimler that are more related to the 3D Experience platform, cloud-based, and also the versioning version of Daimler, which is called the Daimler Power BI or Design with Daimler on the platform. And in this use case, the idea was that there was someone who is a fluids expert and that would develop a library to compute some pressure drops and do some various simulations. And he would push his library and maintain it via this cloud version and versioned Daimler. And then a technical manager would receive a request from a customer to design a certain fluid line hydraulic system. And he would assign a task to someone in his team. And he can do this very easily with some of the applications that we have on the 3D Experience platform. Having this task, the team member receives a notification and starts building a simulation inside the cloud version of Daimler. Afterwards, he asks a review of his work to his technical manager, and the technical manager reviews and asks for modifications. Then the team member does the modifications, and finally the manager will approve. And we will show you right now with the video how this can be done. So here we start with the fluids expert who will use Design with Daimler, which is open like this. on the web page, we have this design with Daimler, and then you have the same look and feel as Daimler, the normal Daimler, but you're connected to a tenant in a collaborative space. And you can take your local Modelica files, put them inside Daimler, and initiate connection with the 3D Experience platform. So this is just to show how the library is. So it's a library for computing static pressure drops. And we start doing our first commit with this user interface, similar to what you can do with Git. And of course, each time you make a change, add a model that you will customize or whatever, you can do several commits, create branches, revisions, and so on. And now we put ourselves into the head of a technical manager here who has created a task and put some specification inside. And he has assigned the task to a team member who will be me, actually. So me, team member, will receive this notification here that I have to do something. Also a message. And I can directly open this object that is called a change action, and I can find my specification inside here. So I read it, blah, 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 and I open System Simulation Designer, which is the app that is fully web-based and that supports Modelica from DassaultSystems. And you see here we have retrieved the package that was pushed by the fluids expert with design with Daimler, and you can assemble Modelica blocks. Note that this is a version of Daimler that is restricted. You cannot do as much things as you can do with Daimler, but you can still drag and drop components, parameterize them, and run simulations. What you cannot do, for instance, is write Modelica code and specific equations and functions. Of course, you can plot curves, bar charts, gauges, any kind of plots, and then create nice cockpits like these and put your curves and so on, and expose parameters. So this cockpit view will then be given to someone who will be called the analyst, but it's either a separate app that is called System Simulation Analysis, or you can use it also in System Simulation Designer. And there, basically the idea is that you can just modify a few parameters and run simulations and also create reports. So this is what is done by the team member here, and he retrieves his report, watches it, okay. And he will then put this report and also this object model inside this change action, so the object that will be used to ask for a review and approval. And there you click here on this small arrow, which goes to in approval. And then you can also notify your manager with a message, of course, but he will, in any case, receive a notification and see an update on his change action. So he can directly there open the report. Oh, he notices that something is not as expected as it was written in the specification. So he tells the team member to add a second branch because there was a second branch missing inside the model. And there he's notified. Okay. He sees that the task has been rejected. He checks why it has been rejected. And there you can directly, okay, go back to the model, create a new revision that will be called revision B, like this. He does the second branch as asked. Here again, you can modify some parameters. Create a report again and update the change action with the version B of the model. And ask for approval again. And Now the manager, technical manager, will be able to review this model again and to approve it because it was a fast process. Now sees the report, everything is fine, he's happy. And he will click on approve, write some meaningful comments. And now that the task has been completed, the team member will receive again a notification and a nice message. And the goal of all this is to see these objects that have acquired the state released, and which makes these objects visible for other people in the company who did not have access to these objects.